very good morning and warm welcome to Online Anesthesia Postgraduate Teaching Program and Zoom platform sponsored by Acrola and hosted by A1 Logics. Today we have two legendary speakers among us. The first topic is Understanding of Anaesthesia Workstation by Dr. Saneesh. He is working as a senior consultant in Ananthapuri Hospital Research Institute, Trivandrum. He is the author of two books, that is Review in Clinical Anesthesia for Postgraduates and Textbook of Anesthesia for Technicians. And he is lot famous in the YouTube channels. He is the founder of Anesthesia Tools YouTube channel. In this YouTube channel, you can watch theory classes, your clinical case discussions, and critical care cases. Everything is available in his YouTube channel. And more than 1 lakh viewers for each YouTube. There is more than 10,000 subscribers are there in his YouTube channel. And he is also the co-founder of the webinar campus and co-ordinator for ICA academics. And his area of interest is e-learning in anesthesiology and critical care, airway management and regional anesthesia. Welcome you, sir, for this online anesthesia forum. Over to you, sir.
Thank you very much. A warm welcome to one and all. I profusely thank Dr. Edward Johnson and his team for giving me this opportunity. I cherish this session because I am sharing the stage with a legend like Gurudatt sir, who is authority in my topic also. So with your permission, sir, and let me start my presentation. Let us move into the business. It's a daunting task for me to attempt understanding Anaesthesia Workstation right from history, parts of anesthesia machine and workstation, and routine checkout procedure. I definitely acknowledge the scientific committee for this opportunity. On this fine Sunday morning, let's go for it, starting with the history of evolution of anesthesia machine. The first anesthetic machines appeared following their public demonstration by Morton in 1846. These initial devices were simple inhalers based on the evaporation of the anesthetic agent. At the beginning of the 20th century, gas machines emerged, facilitating application of an anesthetic flow independent of the patient's inspiratory effort. These machines incorporated technological advances such as flow meters, carbon dioxide absorption systems, and fine adjustment vaporizers. In 1917, Boyle developed this anesthetic machine from Guattmey's basic model and presented it in London at the Royal Society of Medicine in 1918. The original design was composed of a wooden structure in the form of a box which acted as a frame with two transverse bars from which hung the cylinders of compressed gas, 2 of oxygen and 2 of nitrous oxide, an ether vaporizer, and a water flow meter, the bubble bottle from the Cotton and Boothby apparatus. In addition, the machine had a manometer to measure the pressure in the cylinders, sensitive pressure reducing valves, and an alcohol lamp to prevent the nitrous oxide from freezing and thus upsetting the cylinder. The story kept developing, and today we have Anaesthesia Workstation, defined as a system for the administration of anesthesia to patients consisting of the gas delivery system, breathing system, anesthetic gas scavenging system, anesthetic vapor delivery system, anesthesia ventilator, and associated monitoring and protection devices. For easy understanding, why don't we start with the basic Boyle's machine which has only pneumatic components, which are categorized as high, intermediate and low pressure systems. This diagram depicts GE Healthcare Aspire Anaesthesia Workstation gas supply system. The high pressure system extends from the gas cylinders to the high pressure regulators. Red lines around oxygen high pressure section is shown there. The intermediate pressure section extends from the high pressure regulators to the flow control valves and also includes the tubing and the components originating from the pipeline inlets. The low pressure section, which is shown or marked in dashed lines, extends from the flow control valves to the breathing circuit. Now, let us come to what makes the high pressure system. It receives gases from the cylinders at high variable pressures and reduces those pressures to lower, more constant pressure suitable for use in the machine. It consists of hanger yoke assembly, cylinder pressure gauge and primary pressure regulator. The hanger yoke orients and supports the cylinder, provides a gas tight seal and ensures a unidirectional gas flow. The workstation standard requires that there be at least one yoke for oxygen and nitrous oxide. If the machine is likely to be used in locations that do not have pipeline gases, it is advisable to have a double yoke, especially for oxygen. You can identify the body, the swivel gate with retaining screw. This is the retaining screw. The nipple through which gas enters, the Bodox seal, the safety feature index pins of pin index safety system, and inside are the filter and check valve assembly. Here is the diagrammatic representation of hanger yoke assembly. Let us identify the parts once again. The body, which is the principal framework and supporting structure, the retaining screw which tightens the cylinder in the yoke, the nipple through which gas enters the machine, the index pins which prevent attaching an incorrect cylinder, the washer or Bodox seal which helps to form a seal between the cylinder and the yoke. There is also filter to remove the particulate matter and check valve assembly which ensures a unidirectional flow of gas through the yoke. The body of the yoke is threaded into the frame of the machine. It provides support for the cylinders. The swinging gate or toggle gate or swivel gate type yoke, the distal part is hinged. When a cylinder is being mounted onto or removed from a yoke, the hinged part can be swung to the side. Let us have a closer look at how the check valve assembly functions. Please identify the nipple through which the gas enters the machine. Next, identify the plunger that slides away from the side where the pressure is greater. When cylinder pressure exceeds the machine pressure, the plunger moves to the right and gas flows into the machine. Here is how it happens. You can see the plunger moving back and the gas moves into the machine. When the pressure in the machine exceeds that in the cylinder, like in an empty cylinder, the plunger moves to the left, preventing the escape of gas from the machine. These check valves are not designed to act as permanent seals for empty yolks and may allow a small amount of gas to escape. To minimize such losses, a yolk should not be left vacant. As soon as a cylinder is exhausted, it should be replaced by a full one. If a full cylinder is not available, a yolk plug should be placed in the empty yolk. When in place, the plug forms a seal to prevent the gas from escaping from the machine. In the absence of a yolk plug, gas can flow retrograde through an open flow control valve and out through the yolk. Manufacturers often chain the yolk plugs to the machine. Here you can see the yolk plug, which is independent of the pin index system, occupying the empty cylinder slot, guarding against possible escape of gas from the system. Again, it is important that to prevent transfilling between paired cylinders as a result of a defective check valve, only one cylinder of a gas should be open at a time. The Anaesthesia Workstation standard requires that there be a pressure indicator or pressure gauge that displays the cylinder pressure for each gas supplied by the cylinder. The indicator may be located near the cylinders or on a panel in front of the machine. The scale must be at least 33% greater than the minimum filling pressure of the cylinder or the full indication position. Many indicators are of the Borden tube type as shown here. A hollow metal tube is bent into a curve, then sealed and linked to a clock-like mechanism. The other end is connected to the gas source. An increase in gas pressure inside the tube causes it to straighten. As the pressure falls, the tube resumes its curved shape. Because the open end is fixed, the sealed end moves. These motions are transmitted to the indicator, which moves over a calibrated scale. The gauges are required to be calibrated in kilopascals, but pounds per square inch (psi) may also be used. In Anaesthesia workstations, cylinder pressure gauges are seen in the front panel for each gas. Digital pressure readouts are used on some modern electronic anesthesia workstations. The pressure in a cylinder varies. To maintain a constant flow with changing supply pressure, the anesthesia machine is fitted with pressure regulators. A pressure regulator reduces the high and variable pressure found in a cylinder to a lower, more constant pressure suitable for use in an anesthesia machine. Pressure regulators used in anesthesia machines are preset at the factory. One regulator may serve a single or a dual hanger yoke. Here you can see the pressure regulator and the factory set. This is the mainspring, and there is a safety valve also in case excess pressure builds at the level of pressure regulators. Here you can find the nitrous oxide pressure regulator is a slave regulator, since the mainspring in the nitrous oxide regulator is replaced by the oxygen pressure. You can see the tubing getting traced to oxygen pipeline. So, when oxygen line is not pressurized, There will not be any output from nitrous oxide pressure regulator as a safety feature. Now, the intermediate pressure system. It receives gases from the pressure regulator or pipeline inlet to the anesthesia machine. Oxygen may enter the pneumatic components by way of the master switch. When the master switch is turned off, the pressure in the intermediate pressure system will drop to 0. The intermediate pressure system pneumatic components include the pneumatic part of the master switch, pipeline inlet connections, pipeline pressure indicators, the intermediate pipings, the gas power outlet, oxygen pressure failure devices, the oxygen flush, additional pressure regulators or secondary pressure regulators if so equipped, and the flow control valves. The pneumatic portion of the master switch is located in the intermediate pressure system downstream of the inlets for the cylinder and pipeline supplies. The oxygen flush is usually independent of this switch. The master switch may be a totally electronic switch that, when activated, controls the various pneumatic components in anesthesia workstation. Now, the pipeline inlet connection. It is the entry point of gases from the pipelines. These inlets are fitted with threaded non-interchangeable diameter index safety system DIS fittings. In the UK, NIST, that is non-interchangeable screw threaded connection, is used. Each inlet must contain a unidirectional or check valve to prevent reverse flow of gas from the machine into the pipeline system or to the atmosphere if no hose is connected. Each pipeline inlet is required to have a filter with a pore size of 100 micrometer or less. The indicators to monitor the pipeline pressure of each gas are usually found on the panel on the front of the machine and may be color coded for the gases that they monitor. On some machines, the correct range of pressure is indicated by a colored zone also. You can see in the picture. Let us see what happens if the pipeline pressure indicators were on the machine side or downstream side of the check valve. When a cylinder is open and the pipeline supply fails, there will be no change in the pressure on the indicator until the cylinder also is nearly empty. Thus, it will not give a true indication of the pipeline supply pressure unless the cylinder valves are closed. The workstation standard requires that the indicator be on the pipeline side of the check valve in the pipeline inlet. If the indicator is on the pipeline side of the check valve, it will monitor pipeline pressure only. If the hose is disconnected or improperly connected, it should read 0 even if a cylinder valve is open. I hope it is clear. If for any reason the gas pressure coming from a cylinder via a pressure regulator exceeds the pipeline pressure and a cylinder valve is open, gas will be drawn from the cylinder. Therefore, cylinder valves should always remain closed when the pipeline supply is in use. Pipeline pressure indicators should always be checked before the machine is used. The pressure should be between 50 to 55 psig. The indicators should be scanned repeatedly during use of the anesthesia workstation. Now, piping. it is used to connect the components inside the machine. It must be able to withstand 4 times the intended service pressure without rupturing. The leaks between the pipeline inlet or cylinder pressure reducing system and the flow control valve should not exceed 25 mL per minute. If the yoke and pressure reducing system are included, the leakage may not exceed 150 mL per minute. One or more gas power outlets may be present on the anesthesia machine. It may serve as a source of driving gas for the anesthesia ventilator or to supply gas for a jet ventilator. Either oxygen or air may be used, and if there is a choice, there should be a gas power outlet for each gas. In modern anesthesia machines, if the ventilator is an integral part of the machine and breathing system and is connected to the ventilator with an internal piping, therefore, gas power outlet is not found on modern anesthesia workstations. Oxygen supply failure alarm. When the oxygen supply pressure falls below a manufacturer specified threshold, say usually 30 psig or 205 kilopascals, at least a medium priority alarm should be enunciated within 5 seconds. It shall not be possible to disable this alarm. Oxygen pressure sensor shut-off system. It shuts off or proportionately decreases and ultimately interrupts the supply of nitrous oxide if the oxygen supply pressure decreases. When the pneumatic system is activated, oxygen pressure reaches the oxygen failure safety device, allowing other gases to flow. A decrease in oxygen pressure causes the oxygen failure safety device to interrupt the supply of other gases to their flow control valve. Coming to what is SORC, Sensitive Oxygen Ratio Controller System. These are devices that shut off the supply of gases other than oxygen or alarm when oxygen pressure has fallen to a dangerous level. The SORC is a pneumatic mechanical interlock system designed to maintain a ratio of no less than 25% oxygen with 75% nitrous oxide regardless of the operator input. Differential oxygen and nitrous oxide flows and the resultant chamber back pressures determines the position of the nitrous oxide proportionating valve. The SORC requires a minimum oxygen flow of 200 ml per minute for the nitrous oxide proportionating valve to open. Some machines have a gas selector switch that prevents air and nitrous oxide from being used together. That means you can either add nitrous oxide along with oxygen or use a combination of air and oxygen. Oxygen flush receives oxygen from the pipeline inlet or cylinder pressure regulator and directs a high unmetered flow directly to the common gas outlet. This is commonly labeled as O2 plus. In most anesthesia machines, the oxygen flush can be activated regardless of whether the master switch is turned on or off. The flow of oxygen on activating oxygen flush is usually between 35 and 75 liters per minute. Here you can identify the parts of oxygen flush. In the off position of oxygen flush, the ball and spring keep occluding the seat and hence oxygen does not flow to the outlet. Now, let us see what happens when we activate oxygen flush. Depressing the button causes the pin to push the ball away from the seat, allowing oxygen to pass directly to the machine outlet. Here you can see the oxygen flush button is activated, the ball and spring is moved towards the left side, and now when the gas oxygen comes, it can move to the outlet at a specified flow rate. Some machines have pressure regulators in the intermediate pressure system just upstream of the flow indicators. These receive gas from either the pipeline or the pressure regulator and reduce it to further to around 26 psi for nitrous oxide and 14 psi for oxygen. The purpose of this pressure regulator is to eliminate fluctuations in pressure supplied to the flow indicators caused by fluctuations in pipeline pressure. By reducing the pressure below the normal fluctuation range, the flow will remain more constant. Not all anesthesia machines are equipped with this device, that you have to keep in mind. Flow adjustment controls regulate the flow of oxygen, air and other gases to the flow indicators. There are two types of flow adjustment controls, mechanical and electronic. There may be one more type which can be called as transitional, where you will be dialing a flow control knob, but eventually you will get a flow indication in a digital format on your screen. Mechanical flow control valve controls the rate of gas flow through its associated flow meter. Mechanical flow control valves are used with both mechanical and electronic flow meters. The flow meters are mounted vertically and usually next to each other in such a way that the upper or downstream end discharges into the manifold. Turning the stem of the flow control knob creates a leak between the pin and the valve seat, so that the gas flows to the outlet, pushing the bobbin or float upwards. The stop collar prevents over tightening of the pin in the seat. Now we come to the third part, the low pressure system. Low pressure system is downstream of the flow control devices. The pressure in this section is only slightly above the atmospheric and variable depending on the flow from the flow control valves. The components found in this section, that is low pressure system, include the flow meters, there are some hypoxia prevention safety systems, the pressure relief valves, the unidirectional valve and then the common gas outlet. As you have seen, the vaporizers and their mounting devices are found in the low pressure system. The traditional mechanical flow indicators used in anesthesia machines have been of variable orifice or Thorpe tube type. A vertical glass tube is internally tapered with its smallest diameter at the bottom. It contains an indicator that is free to move up and down inside the tube. When there is no gas flow, the indicator rests at the bottom of the tube. Gas entering the side tube pushes the bobbin up in proportion to the gas flow. The bobbin floats and rotates inside the side tube without touching the sides, giving an accurate indication of the gas flow. The side tube is made leak proof at the top and bottom of the flow meter block by O-rings, neoprene sockets or washers. The vertical rotameter is an example of constant pressure variable orifice flow meter. Its operation is based on the principle of Thorpe tube. This rotameter consists of three elements: a uniformly tapered flow tube, the Thorpe tube, a bobbin or float, that is the marker, and a measurement scale. The tube is positioned vertically with its smallest diameter end of the tapered flow tube at the bottom. Because the annular space is tubular at low flow rates, the flow is laminar and viscosity determines the gas flow rate and hence follows the Poiseuille's law. The annular space simulates an orifice at high flow rates, and turbulent gas flow then depends predominantly on the density of the gas and follows the Graham's law. The indicator, the float or bobbin, is a free moving device within the tube. A rotating indicator is giving an evidence that the gas is actually flowing and the indicator is not stuck. When gas passes between the rim and the tube wall, the fluid causes the indicator to rotate between the rim and the tube wall. The fluids cause the indicator to rotate. You can note that whether the flow indicator float is in the shape of a ball or a bobbin, flow on the calibrated scale should be read at the highest and widest portion of the float. Here you can see different positions where you read the measurement of gas flow. Recent increased interest in low flow anesthesia systems have created a demand for flow meters that can more accurately measure the flows below 1 liters per minute. This is achieved by the use of two flow meter tubes for the same gas. The first is a long thin tube accurate for flows from 0 to 1000 mL per minute that complements the second conventional tube calibrated for higher flows 1 to 10 liters per minute or more. Both are activated from the same flow control valve. These cascade flow meter tubes for each gas are arranged sequentially so that the flow control valve, when the flow control valve is opened, the low flow tube is seen to register first. At flows over 1 liters per minute, the bobbin in the low flow tube is no longer easily visible. Here you can find the knob for oxygen is color coded white, fluted and larger in diameter than the other gas flow control knobs. The nitrous oxide control knob is smaller, blue in color and ridged, but not fluted like oxygen knob. Positioning of the oxygen flow meter in the bank of several gas flow meters is important. The Anaesthesia Workstation standard requires that the oxygen flow meter be placed on the downstream side of the flow meter group when the workstation is viewed from the front. It is also the most downstream flow meter closest to the common gas outlet to make hypoxia less likely in the event of a leak in one of the other flow meters. Okay. If there is a leak in a flow meter other than oxygen, at least oxygen should be flowing directly to the common gas outlet. This is an anti-hypoxia safety feature. Anesthesia machines in use now must either not be capable of delivering a gas mixture less than 20% of oxygen or have a means to give an alarm at an oxygen concentration of below 20% in the inspiratory gas. The mechanism may be a pneumatic one, mechanical one or electronic one. The Omeda Link 25 system incorporates a chain that links the flow control valves for nitrous oxide and oxygen. There is a mechanical linkage as well as a pneumatic linkage. There is a 14 tooth sprocket on the nitrous oxide flow control valve and a 29 tooth sprocket on the oxygen flow control valve. Thus, for every 2.07 revolutions of the nitrous oxide flow control spindle, an oxygen flow control set to the lowest oxygen flow rotates once. The proportionating of nitrous oxide to oxygen 75% to 25% is completed because the nitrous oxide flow control valve is supplied from a second stage gas regulator that reduces the nitrous oxide pressure to a nominal 26 psig, adjusted as previously described before it reaches the flow control valve. The oxygen flow control valve is supplied at a pressure of 14 psig from the second stage oxygen regulator. So, now after mechanical and pneumatic linkage, you get oxygen and nitrous oxide flow control valves effectively maintaining a minimum of 25% oxygen. Now, we look at the pressure relief valve. As the name suggests, it prevents buildup of excessive pressures upstream of the outlet check valve. This valve opens to the atmosphere and vents out gas to the atmosphere if the preset pressure is exceeded. Unidirectional or check valve is located between the vaporizers and the common gas outlet upstream of where oxygen flush flow joins the fresh gas flow. The purpose of the outlet check valve is to prevent reverse gas flow, a situation that would permit fresh gas to re-enter the vaporizer. Thus, it prevents the pumping effect. Now, we come to the common or fresh gas outlet. It receives all of the gases and vapors from the machine and delivers the mixture to the breathing system. Most outlets have a 15 millimeter female slip joint fitting that will accept a tracheal tube connector with a coaxial 22 millimeter male connector. It can be via ACGO, auxiliary common gas outlet, or outlet for connecting the circle system breathing circuit in anesthesia workstations. This is in brief regarding the parts of anesthesia machine. I would like to acknowledge Sultan Qaboos University Hospital, Muscat and Ananthapuri Hospital, Trivandrum, Kerala for providing the clinical materials for photo and videography. Now, before concluding, let us go through the routine checklist for anesthesia workstation. In the recent past, it was easier to perform a pre-anesthetic checkout on an anesthesia machine. The machines were not as complicated and the checkout did not differ much from one type of machine to another. There was a list that you could either commit to memory or attach to the machine as a guide, and you had to complete each step similar to an airline pilot's pre-flight checkout. Things are much different now. Not only are there many more models of anesthesia workstations with different features, but some machines do an automated checkout. Let us see the checkout procedure before the first case of the day for Datex Omeda Aspire machine. Modern anesthesia workstations have pneumatic components as well as electrical components. So, our machine checklist starts with making sure that our machine is plugged in, switched on, and adequate battery backup is ensured. Check the high pressure system. Check with a tuck test that each pipeline is correctly seated and in the appropriate wall outlet designated for the specific gas. See that pipeline pressure gauges read 50 psig of pressure. Right now cylinder pressure gauges should read 0. Now identify the cylinders by color coding or label and ensure proper mounting. All the cylinders should be in off position. Regarding oxygen cylinder, you need to open the oxygen cylinder. See that the cylinder pressure gauge reads at least half full or 1000 psig after opening the cylinder. After that, keep the oxygen cylinder closed. Next step is checking for circuit leak in the anesthesia machine ventilator circuit. The machine as of now is in the off position. Select the back selector switch to ventilator mode. Take the circuit, occlude the distal end or the patient end of the circuit, and then using oxygen flush, inflate the bellows and keep the circuit occluded. Make sure that the pressure gauge shows less than 15 centimeters of water and the fall in the bellows is less than 100 ml per minute. Next step is low pressure leak test. Before you start low pressure leak test, make sure that all the flow meters are off, all the vaporizers are off, and you need low pressure leak test device. This is also called as universal leak test. This has got a suction bulb and an inlet. And the first step will be to check this equipment for any leak. First, make a good finger seal at the inlet and repeatedly squeeze the bulb so that this bulb is collapsed, and this bulb should stay collapsed for at least 60 seconds. Change the back selector switch to back mode. Change the circuit selector to auxiliary circuit and then attach the leak test device. Squeeze repeatedly so that the bulb is collapsed and make sure that the bulb stays collapsed for at least 10 seconds. You have to repeat the low pressure leak test after opening each vaporizer one at a time. After the leak test, see that the circuit selector is switched back to closed circuit mode. At this stage, you can turn the machine on. Check that flow rotometers operate smoothly and bobbins move freely throughout its range. Now checking for anti-hypoxia safety features. Increase the nitrous oxide flow. Note that oxygen flow meter automatically turns on. Now reduce the oxygen flow up to 0. Note that nitrous oxide also automatically comes down to 0. See that the machine shows FiO2 more than 21% throughout the full range. To check for oxygen failure alarm, set the oxygen, nitrous oxide and air flow to mid-range. Disconnect the oxygen pipeline. See that nitrous oxide and oxygen flows reduce consistently, but oxygen flow comes down the last. Air flow continues and oxygen failure alarm should go off. Now reconnect the oxygen pipeline. Next step is to calibrate oxygen sensor. Navigate using menu bar to oxygen calibration at 21%. Remove the breathing circuit. Open the panel as per the manufacturer's instructions. Identify the oxygen sensor. Remove it by rotating counterclockwise and expose the sensor to room air. Push the knob to start calibrating. It takes a while to complete the calibration. Once completed, reinstall the sensor, rotate clockwise. Now replace the panel carefully. The oxygen analyzer is calibrated at 21%. Now increase the FiO2 by using oxygen flush and see if the oxygen sensor reads above 90%. Next, we'll check the vaporizers. Check that each vaporizer is adequately filled and not overfilled. Check that each vaporizer is correctly seated onto the back bar. See that the locking mechanism is fully engaged. The control knobs rotate fully throughout the range. Because of locking mechanism, only one vaporizer can be turned on at any time. Check the breathing system for correct configuration, inspiratory limb, expiratory limb, and check the soda lime canister whether it is exhausted. Next step, change the ventilator parameters depending on the first phase of the day, appropriate settings, and now you take the test lamp and connect it to the patient end of the circuit. The back selector switch should be changed to ventilator mode. Minimum oxygen flow meter settings are there. Using the flush, fill the bellows, and now the machine ventilator starts. Check whether ventilator displays correct data. The end expiratory pressure should read 0. Note that the bellow inflates and deflates, and check whether the bellow fills completely. Check the correct operation of unidirectional valves. The inspiratory valve rises on inspiration and falls in expiration. The expiratory valve rises in expiration and falls in inspiration. Now disconnect the test lamp. Check whether disconnection alarm is working. Now we'll check the manual ventilation system. Test lung is connected. Increase oxygen flow to around 5 liters per minute. Set the back selector to back mode. Set the APL valve to 30 and ventilate manually. Check for inflation and deflation of the test lung by way of appropriate feel of resistance and compliance. You have to check again for the functioning of the unidirectional valves. To test the back circuit for leak, remove the test lung, occlude the patient end of the circuit, close the APL valve, and using minimum oxygen flows, using oxygen flush, pressurize the circuit to around 30 centimeters of water and see that it is retained for at least 10 seconds. After 10 seconds, open the APL valve and see that the pressure monitored in the gauge goes back to 0. Now we can check for auxiliary oxygen. While occluding the auxiliary oxygen outlet, the bobbin tip, remember to close the auxiliary oxygen flow meter. Check whether suction source is connected and the suction regulator provides adequate suction. See if the scavenging circuit is appropriately connected and switched on. The AGSS indicator should be in the green sector. The machine checkout is complete when you make sure we have the final position and ready to go for the first case. Make sure that all the flow meters are off, your vaporizers are off, APL valve is fully open. Make sure adequate suction, appropriate breathing circuit and mask is attached, and you have an alternate means of manual ventilation in case of any equipment failure with an independent source of oxygen. You are ready for the first case. That was the routine checkout procedure for that particular anesthesia workstation. I agree that the discussion is neither complete or exhaustive. I have tried my best to be within the schedule of time allotted. The topic is very vast and of course very important too. I thank the organizers, Dr. Edward Johnson and his team for the opportunity. I would be happy to take questions with the best of my abilities.
Thank you, sir.
Thank you very much.
Thank you, sir. It was a wonderful presentation. I think PGs must have enjoyed it well. And there are a few questions, sir. The first question is about jet ventilation and how to connect it to the workstation.
Okay. Regarding jet ventilation, what I think is nowadays our modern anesthesia workstations, we don't get the gas power outlet. If gas power outlet is there, you can connect to that because it comes with a intermediate pressure system pressures to charge the to provide the high flows. Otherwise, what we can do is we can connect the jet ventilator system to the oxygen flush and use the oxygen flush switch for activation. And if you have a Sanders jet ventilator, probably you can go to the wall outlet and connect directly to the wall outlet oxygen and use the jet ventilator rather than struggling with the oxygen flush, where you will be struggling with the dual control. Gurudatt sir, any input, sir?
Yeah, what you said is very clear that jet ventilator, if at all, if you want to connect, so you can connect it to the common gas outlet and then use the oxygen flush button, so that you can try. But nowadays, the requirement of jet ventilator has come down drastically, because in the olden days we used to go for cricothyrotomy and using a needle cricothyrotomy. Now we don't use a needle cricothyrotomy. We go for regular cricothyrotomy. We put a tube there and we start ventilating. So that's how the majority of the hospitals will not have a jet ventilator nowadays.
Now we are in the era of front of neck access.
Yeah, front of neck access is there. Because during those years, the needle cricothyrotomy used to be done and the use of jet ventilator was required.
Yes. Thank you, sir.
Yeah.
Thank you, sir. The next question is on minimum mandatory flow of oxygen.
Yeah, actually in this talk, I haven't dealt with the safety features, because if we start describing all the features, I think it's a 2 or 3 day session. So minimum mandatory flow is the manufacturer specified a given rate, which will ensure that maybe 25 mL per minute or 200 mL per minute as per the manufacturer specification will be provided continuously as long as the workstation is switched on. The moment you switch on the master switch, this much oxygen will be flowing irrespective of whether you activate oxygen flow control knob or not. This is a safety feature, because sometimes people tend to forget about switching on oxygen and start holding the mask. So at least 200 mL per minute of oxygen will be flowing. So this is a safety system. And during the checklist, I have mentioned that when there is a minimum mandatory flow of oxygen in a given anesthesia workstation, you will be keeping the master switch off when you are checking for the leak. Otherwise, the moment you switch the master switch on, 200 mL will be anyway getting provided. So that might cover up the leak. So you close the master switch and then do the leak test. So minimum mandatory flow is an anti-hypoxia safety feature, which is mostly provided in the modern anesthesia workstations.
Dr. Saneesh, nowadays we don't have this minimum mandatory.
Newer machines.
They have removed it actually,
Mm-hmm.
because it could produce what was called as a Monday morning sickness. I would be talking about that in my talk. I think I'll clear that.
Okay.
Nowadays we don't have minimum mandatory flow of oxygen at all.
It will also interfere the low flow anesthesia also.
Yes, sir.
Thank you. Next question.
There is one more question on nitrolock, sir.
Yeah, nitrolock, I think it's all about, we are mentioned as a nitrous oxide regulator as a slave regulator. So nitrolock basically means when oxygen line is not pressurized, there is no output from the nitrous oxide pressure regulator. So this is again one of the safety mechanism, and different manufacturers coin different patented names for these safety features, just like we speak about Link 25 of Omeda.
But in the older machines, Dr. Saneesh, we used to have a trilene lock.
Yes, trilene lock is a different thing.
Yeah.
Where we want to isolate when trilene is used, soda lime should be isolated.
Exactly. Because phosphine, which was a neurotoxic agent, would be produced with reaction of trilene with the soda lime. So
Yes.
that's how, we stopped using trilene. Now that's how the trilene lock also has been taken off.
I think the people who are into the residency these days, if they happen to see trilene lock, they are blessed, because not many institutions can provide the basic boils apparatus to study this.
Correct.
Modern workstations, everything is covered up. You don't have an opportunity to open it up and see how oxygen is deviated from its pressure regulator to different portions and all. Older machines, we can open the lid and see how the oxygen piping is branching and where all it supplies and all. This is one of the favorite question also, like where all oxygen.
Nowadays we used to keep it in museum.
Yes. So that has to be preserved for the upcoming generation.
Can we take one more question, sir? There is one question asking in which system the flow meter is placed, is in the intermediate and the low pressure system?
See, up to the level of flow control valves, that is the boundary. So when in a closed position, that is the boundary. Okay, beyond that, whatever is there downstream will fall into the low pressure system when the flow control valves are closed. So
actually,
when you activate,
all these things are just arbitrary things. So
yes,
we need not have to, fix our idea. Okay, till this level is low pressure system, or till this level is intermediate. We need not, just for description sake, that it has been made.
Yes.
Sir,
one more question.
Yes, sir. Why you should not open the two vaporizers at a time?
Okay, then that's an interesting question. Like if you use only one vaporizer at a time, actually the fresh gas will flow through the bypass chamber or the vaporizing chamber of one agent and then will carry the vapor. If two are open, this vapor molecules will also get into the vaporizing chamber of the next vaporizer. So there will be intermixing, or say probably we can term it as a cross contamination of the vapors. So the problem is, we'll not be sure when this second vaporizer gets freed of the previous vapor molecules. So if we have a gas analyzer, most of the gas analyzers will identify the vapor molecules by its structure itself and will display on the monitor as per the color code. Say for example, if you are opening sevoflurane, it will be displayed on yellow digits like 2.1, 1.8 like that. When we switch over to desflurane, there will be a transition period when even it may be shown in a violet color and then it will turn to blue color. So even those mechanisms will find it difficult to identify the agent. That is one thing. Cross contamination is the other thing. I'm not aware about any other major mishaps except for keeping the vaporizing chamber clean and uncontaminated for subsequent use. Gurudatt sir, any input from
Yeah, that is the main thing. And but sometimes, in the exam for the students, they will be asked, so how to arrange these vaporizers? So because, in olden days, it was a very common question. Of course, nowadays, there is no question of these things because we have locking system so that you cannot open two vaporizers at a time. But just for the sake of the postgraduate students, if that type of a question is asked, high potency vaporizer should be always in the downstream. So low potency vaporizer should always be in the upstream. So suppose even if I open both the vaporizers, So the low potency vapor, even if it collects into the high potency, the inhalation anesthetic agent, when we use the high potency volatile anesthetic agent, there won't be any problem for the patient. If it is the opposite, high potency, because I'm very low MAC, so it can produce problems for the patient when you are opening a low potency vaporizer. So that is the one answer the students have to talk about.
Yes.
The same question, sir. Can we use one vaporizer? We can use isoflurane and sevoflurane alternately in a case. The same case, we can use isoflurane for some time and sevoflurane for some time.
Many places people are using it, but I think Miller specifically mentions like you want to save the cost, you want to have a faster recovery. So can we use halothane throughout the case and simply switch over to sevoflurane or desflurane at the end of the case for faster recovery? They have mentioned that you can't. It's like saying, can I have my cake and eat it too? So both you can't get, but of course some anesthesiologists will be practicing it, but there will be a transition time, because if you are using a longer acting inhalation agent for some time, it will take its own time for the recovery. It will not happen just like that, because our agents are going to be stored in the other compartments inside the body, not only the vessel rich group. So if you use say halothane for some time, it has to come out from other compartments into the lungs and get exhaled. It will take its own time.
So, Professor, take all the questions.
Yes, sir. There is one question: if we use the flush and fill the billows, will there be a barotrauma when the patient is connected to in the circuit?
And that's commonly discussed. I think these are some of the apparatus which will act as a pressure buffer. Your bellows, your reservoir bags will buffer most of the additional excess pressures inside the system. So though it's not advised, but good amount of excess pressure will be buffered by reservoir systems. Even your breathing circuit will buffer additional pressure for some time to an extent.
So, but one more thing, Dr. Saneesh, is that in Draeger machines, we do have fresh gas flow decoupling system.
Yes.
So that the inspired gases will not go to the patient at all. The inspiratory gases or the fresh gas flow directly will go to the bag. So that even if we activate the flush, so the bag will distend, because whatever the valve is there, it will not allow the gases of the flush directly going to the patient. So that's how there won't be any barotrauma. This particular safety feature has been adopted in Draeger machines. In case of GE machines also, because there is a pressure relief valve is there, so any increase in pressure in the system, suddenly more than 60 centimeters, it opens up and then does not allow the gases to move into the patient's lungs. So that way, these two mechanisms in different either GE system or the Draeger system we have.
That's why even oxygen flush, we cannot continuously activate unless we are doing it intentionally. Because the moment we release the button, it comes back and switches off the high flow of oxygen.
So in some of the older machines, you must have seen there was a lock also for oxygen flush. So that was very dangerous actually. So that has been taken off later.
Okay.
There is one question asking what is the difference between a common gas outlet, gas power outlet, and auxiliary oxygen?
Okay, common gas outlet is the fresh gas outlet, the final outlet of the anesthesia machine. Second one is gas power outlet is a part of the intermediate pressure system which will power the anesthesia ventilator. Previously, the ventilator units used to be a different one. It was not part of the machine. So that ventilator used to be powered, the driving gas used to be powered from the intermediate pressure system through gas power outlet. Auxiliary oxygen is just like providing a flow meter outlet of just like your wall outlet. Even if you put a flow meter onto your wall outlet and open the oxygen, you can simply connect to the Hudson's mask or the other Venturi mask or whatever. So that outlet is auxiliary oxygen. Okay, some of the machines, newer machines, auxiliary oxygen is outlet is provided separately. So in the checklist, I have mentioned how to check whether auxiliary outlet is oxygen outlet is working. Just occlude it intermittently and see whether the bobbin goes up and down when you switch on the auxiliary oxygen. So basic funda is whichever machines you are using, you should know your machine before using it. You should know the features in it. What are the safety features? That's the idea of having a specific or unique checklist for that particular machine, so that you will also be sure which all anti-hypoxia devices or which all options are available. Some of the workstations will provide you with the suction outlet also. So the vacuum pressure gauge is also seen on the front panel, like the machine I showed during the anesthesia machine checklist. So you can check the adequate suction also coming from the anesthesia workstation. So know your machine, know the features, know which all outlets are providing what, and then start using it for your anesthesia service.
Thank you, sir. With that, we will move on to the next. Thank you very much, sir. Saneesh, sir.
Thank you very much, sir. Thank you very much, sir.
So we move on to the second topic, that is understanding of breathing circuits by Dr. Gurudatt, sir. He needs no introduction among postgraduates. He is doyen of anesthesiology field. Presently, he is working as the professor and head of Department of Anesthesiology, Critical Care and Pain Medicine, JSS Medical College, JSS Academy of Higher Education and Mysore. He was awarded, he received many awards. That is Eminent Anesthesia Teacher Award 2021 by ISA, Karnataka State, and Neon Excellence Award for Education Initiatives in 2017. And he received Best Teacher Award in the year 19, 20, and 21. He served in Indian Army as captain for 5 years. He is the former professor and HOD of Mysore Medical College. And he is the associate editor of IJA for the past 6 years. And he is the member of advisory board of IJA and KJA from 2011 till date. And he is the advisor to the scientific committee of ISA Karnataka. And he is a member of board of studies of Mahatma Gandhi Medical College and Research Institute, Sri Balaji Vidyapith University, Pondicherry. He had published more than 42 national and international publications, and he has attended more than 200 invited lectures. So welcome you, sir, for this online anesthesia forum, sir. Over to you, sir.
Thank you, Dr. Johnson. I'll share my PPT. Just a minute. Good morning, everybody. And first of all, I would like to thank Dr. Johnson for this excellent opportunity that has been given to me to discuss about the understanding of anesthesia breathing systems. And also, I would like to bring greetings from the JSS Medical College Hospital, where presently I'm working. You know, the breathing systems are very important for the postgraduates because this forum is basically for the postgraduates, and you know, every day they are using anesthesia workstations and also anesthesia breathing systems. So they have to know about these breathing systems because, you know, once they understand these breathing systems properly, they can be very safe to the patient. The other advantage of knowing about the breathing systems is because, you know, a lot of questions will be asked both in theory as well as in practicals for the postgraduates. So it is always better they have a sound knowledge about these breathing system. So the objectives of this particular lecture of mine is mainly to make the students understand the brief history of the breathing systems, the definition of breathing systems, functions, the requirements, the importance of different components, the classification, how to classify these breathing systems, the functional analysis of Mapleson systems, and also details about the closed circuit. So whatever I will be describing or discussing, so mainly in terms of the examination of the point of view and what common questions will be asked regarding these breathing systems. So when anesthesia was introduced to the world by W.T.J. Martin, that was on October 16, 1846. So, the Martin did not use any breathing system at all. You can see here, Martin providing anesthesia to Gilbert Abbott. He was the first patient where the public demonstration was done, and Warren and Bigelow were the surgeons. And of course, there was no breathing system was used. So for many years, so this was the type of anesthesia that was given, and there was no need for breathing systems. Till, when Sir Henry Edmund Gaskin Boyle introduced the first anesthesia machine, that was in 1917. So there was a requirement of a breathing system which could connect the machine to the patient, and all the anesthetic and plus the oxygen could be provided to the patient. So this particular requirement was fulfilled by Sir Evan Whiteside Magill. That was in 1917. Sir Magill is considered as the father of modern anesthesia. So he has many contributions. So one of the contributions is a circuit which is called as a Magill circuit. Now presently it is called as, after the classification by Mapleson, it is called as the Mapleson A circuit. But during those days, the problem was, there were many cases of the patients with a lot of infections, especially the tuberculosis was rampant. And when these circuits, those circuits were, reusable circuits, there were no disposable circuits now like presently we have. So they had to reuse the same circuit for the patients without infection also. So they had an apprehension that, the infection could be transmitted by these circuits. So that's how there was a requirement of some equipment and a circuit wherein it could be autoclaved and then reused. So that's how this was fulfilled by Ralph Milton Waters. That was in 1927. He introduced what is called as, the to and fro circuit. So the to and fro circuit, many times this also will be kept for you in the exam in many of the practical centers. So this canister that he was using, so this canister is fully made of stainless steel and could be autoclaved. Even the expiratory valve, the inlet for the fresh gas flow, everything is made of steel. So the whole thing after it has been used for an infected patient could be autoclaved. So that's how, this was highly useful during those days. And, Waters was the first person to use soda lime for absorption of carbon dioxide and reuse of expired gases. So based on this idea, in 1930, Briansford introduced the circle system. I always considered this particular introduction of the circle system as a revolutionary introduction because, it is almost nearly 92 years. Now also we are using the circle system. And because of Briansford's introduction of the circle system, now we are able to go for low flow technique. And how important it is to go for low flow technique. And there are so many advantages of low flow technique. So, but again, during those days, another problem was we had only either Mapleson case, that is a Magill circuit, the closed circuit, or the to and fro circuit. But for pediatric purposes, especially during those days, the common surgery that was done in pediatrics was cleft lip surgeries. So if you connect these kind of circuits, which were very heavy, so majority of the times the dislodgement of the endotracheal tube was very common because they used to drag on the endotracheal tube. So there was a requirement of a circuit which will not produce any dragging on the endotracheal tube that could be used in pediatric age group. So that's how Thomas Philip Eyre in 1939 he introduced the Eyre's teepees. So this IRSTP is, the one end you connect to the patient, other end the fresh gas flow is there. The opposite end of the patient, it's for expiration of the gases. So that's how it became quite popular. But the disadvantage with the IRSTPs was, the corrugated hose was very short and it was not providing a reservoir for the tidal volume of the child. And the other problem was controlling the ventilation was very difficult because there was no bag. So again, this was modified in 1952 by Gordon Jackson Rees. So what he did was he extended the corrugated hose and also added a bag, and of course without a valve. So valve would provide extra resistance to the child's breathing, because during those days spontaneously breathing children or the spontaneous ventilation was commonly used. So in order to prevent any extra resistance and any extra work-up breathing, so he had not used any valve for this modification of the IRSTPs. That's how even today we are using the Jackson-Rees modified IRSTPs. Of course, it was later classified as the Mapleson F circuit by Wilson. So again, many of these open circuits were actually classified by Mapleson with the English alphabets from A to E. So he was actually, Bill Mapleson was a physicist. So he had done a lot of experiments on these breathing circuits, especially the functional analysis of all these circuits were studied by him. And then, because of him only, we know how each of the circuit requires how much of the fresh gas flow. So he lived for almost nearly 92 years. About 4 years back, he passed away. So one thing I just want to show you, this is the handwriting of Bill Mapleson. So in UK, so one of my students went for a conference where Bill Mapleson was there. He was already nearly 90-year-old. So she thought immediately about me and she bought a physics book. And what she did was she asked Bill Mapleson to write a few words towards me. So he has written this, that to Dr. Gurudatt, may you enjoy your career in anesthesia as much as I have. Bill Mapleson, his signature. So it's a prized possession for me, and I keep showing out to all my postgraduates regarding this particular handwriting of Bill Mapleson. Again, all the circuits were used to be very heavy. They had all metal connectors. So especially for head and neck surgeries, it was very difficult to manage because of the dragging on the endotracheal tube. That's how the coaxial circuits were introduced. The first coaxial circuit was introduced by Bain and Sporrell in 1972. So actually, in their article in the Canadian Journal of Anesthesia, Bain and Sporrell, they wrote that surgical procedures about the head and neck require an anesthetic system which is light in weight, does not create facial distortion, and does not cause excessive drag on the endotracheal tube. It was very true, and Bain circuit became extremely popular. Even today, we are using Bain circuit, so almost for many of the surgeries. So another coaxial circuit was introduced by Alistair Lack. So we know that Bain circuit is a modification of Mapleson D, whereas the Lack circuit is a modification of Mapleson A. So actually, Alistair Lack was called as or nicknamed as the Flying Doctor. He introduced this Lack circuit in 1976. So he used to work for the anesthesia department and emergency department. He was a firm believer that wherever accident happened, so first thing we have to attend these patients there and there exactly at where the accident has occurred, so that the golden hour of trauma he was already knowing. So he used to travel immediately there, stabilize the patients, and he used to bring the patients to the hospital. That's why he was nicknamed as Flying Doctor. This is a brief history of the breathing circuits. Let us move on to the definition of breathing circuit. Now, the definition of breathing system is the system is a set of components joined together which makes a connection between the patient and the anesthesia machine. Actually, by connecting the machine to the patient, they form an artificial environment through which the patient will be breathing in and out. So the patient will be totally disconnected from the external environment. Now coming to the functions of the breathing system. So the main functions of the breathing system is, the oxygenation of the patient, effective carbon dioxide elimination. These two are the most important functions. That is the reason why we also have so many safety features in the Anaesthesia Workstation also. And the third is the carry anesthetic mixture to the patient. Now these breathing systems, we know that there are a lot of requirements are there for when I want to use a breathing system. So these requirements can be classified as essential requirements and also desirable requirements. So what are the essential requirements of a breathing circuit? One thing is the breathing system should deliver the gases from the machine to the alveoli in the same concentration as set and in the shortest possible time. So this is very, very important, because whatever we set the concentration at the vaporizer end, so the same concentration should reach as early as possible to the patient end of the endotracheal tube, so that the concentration of the vaporizer and the concentration at the patient end should be equilibrated as fast as possible, so that the induction can be faster. So the other thing is the breathing system should not absorb this inhalation anesthetic agent, so that the concentration at the vaporizer outlet should be the same concentration at the patient end also. So this is one of the essential requirements of a breathing circuit. So the second thing is there should be minimal rebreathing of carbon dioxide. So this is another very important thing, because rebreathing of carbon dioxide will produce hypercapnia, and that all the problems of hypercapnia to the patient can occur. The third is there should be a minimal resistance. So again, if the breathing system, especially when you allow the patient to breathe spontaneously, if the breathing system itself is producing increased resistance, the patient has to work more to counter this resistance, and this can definitely produce gradually hypoventilation, and again hypercapnia can occur. So what are the desirable requirements of a breathing circuit? So one thing which is very, very important is the economy of fresh gases. So actually, we talk about the breathing system, whether it is an ideal for a particular type of ventilation is based on how much of fresh gas flow we have to use. So that's how the economy of fresh gases are very important. The other thing is, we know that in closed circuit, when we go for low flows, definitely so much of economy of fresh gases as well as the inhalation anesthetic agents will be there. So the next desirable one is the conservation of heat and adequate humidification of inspired gases. So what we use, the gases are all dry gases. So because we are using dry gases, there is always a possibility of tracheitis, laryngitis, bronchitis, and the patient can have all these problems in the post-operative period. So that is the reason heat and humidification of inspired gases is very important. So that's how it should be able to provide heat and adequate humidification of the inspired gases. It should be of lightweight. That if it is not lightweight, already I discussed, it can drag on the endotracheal tube. And another thing is it should be efficient during spontaneous as well as controlled ventilation. And also it should be able to be used for adults, children, and also should be able to be used along with the mechanical ventilators. So that's how the system should be a universal system. Of course, till now, we don't have any breathing system which can satisfy all these requirements. Of course, the closed circuit almost comes very close to meeting all these requirements. So one more requirement is, of course, the provision to reduce theater pollution. Of course, that is depending on the scavenging system. So what are the components of breathing system? So we have the components like the reservoir bag, the fresh gas flow entry, the expiratory valve, the corrugator tubing, unidirectional valve, and the carbon dioxide absorber. So among them, the unidirectional valves and the carbon dioxide absorbers are mainly present in the circle system. So I'll be discussing about these two when I discuss about the circle system. So whereas these four, components, actually by varying or changing their position in the breathing system, you can have different Mapleson systems. So you can have A2, F based on where is the fresh gas flow entry, where is the reservoir bag, and where is the expiratory valve. So that's how They are so important. Their position is also so important as far as a breathing system is concerned. So let us discuss about the importance of each one, because in the exam you will be asked about the each of these components individually. That's why it is better to know about each one of them. So coming to the reservoir bag. So we have various sizes of this reservoir bag. We have a half liter bag, 1 liter, 2 liter, and 3 liter bags. So how do we know which particular size of the bag we can use for a particular patient? So this is basically based on the inspiratory capacity. Again, this is an exam question, so you should always be able to know about it. So the inspiratory capacity is roughly about 30 to 35 ml per kg. You know, inspiratory capacity is a combination of inspiratory reserve volume and the tidal volume. A patient can maximally breathe at a time to his inspiratory capacity. So if the bag can provide this amount of reservoir for the patient, even if he breathes to his inspiratory capacity, then it is an ideal size of the bag. So sometimes, you know, even if the bag size is higher than the inspiratory capacity, also no problem. You can still definitely use, but you cannot use a bag which has got a inspiratory, the bag size of less than the inspiratory capacity of the patient. So why you can still use a higher size of the bag more than the inspiratory capacity is because as long as it can provide that amount of the volume for that particular breath, it is fine. But the thing is, we cannot use a 3 liter bag for a child where the half liter bag is ideal. That is because the problem is, if I want to control the ventilation, it will be so difficult to control the ventilation. I don't know how much of the tidal volume I am producing when I am using a 3 liter bag for a, say, a 5 kg child. The other thing is, if I am leaving a child on spontaneous ventilation, I will not be able to know whether the bag is moving or not. So that is the reason it is always better to check or to have or select a particular bag based on the inspiratory capacity of the particular patient. Now, what are the functions of the reservoir bag? So it acts as a reservoir, as the name itself is a reservoir bag. So it acts as a reservoir for the peak inspiratory flow rate of the patient. So this is one answer that is, all the examiners want you to talk about. You just cannot say it acts as a reservoir. It acts as a reservoir for what? So it acts as a reservoir for the peak inspiratory flow. So what is this peak inspiratory flow? It is usually about 3 to 4 times the minute ventilation. So why it is important is, suppose I'll give you an example wherein we are using, the patient is having a tidal volume of about 500 ml and he is breathing at a rate of about 20 breaths per minute with an IE ratio of 1:2. So that means this, each cycle is about 3 seconds and inspiration is for 1 second and expiration is for 2 seconds. So if the inspiration is for 1 second, that 500 ml of the gas should be delivered to the patient in that 1 second. That means the flow rate has to be minimum of 30 liters. But what is the flow rate we fix on our, the flow meters? Usually maximum 4 to 6 liters will be fixing. So that's how, the reservoir bag will always be providing whatever the extra flow the patient requires because of the, the gas that is present that gets accumulated during expiration. So the second function is, visual and tactile assessment of respiration and depth of anesthesia. I still remember during our days when we used to leave these patients on spontaneous ventilation, we just used to hold the bag in our hand. So once we are holding the bag in our hand, we need not have to look at the bag to know what is the depth of anesthesia the patient is in and whether he is adequately breathing or not. So this is a very important function of the bag. The third is, for controlling the ventilation. So if we don't have a bag like Mapleson E circuit or, IRS TPs, there is no bag and very difficult to control the ventilation. So if a bag is there, easy to control the ventilation. So you can even nebulize sometimes certain drugs like bronchodilator. Suppose if you don't have a TPs, you don't have a nebulizer, so you can just pour the bronchodilators into the bag and start ventilating the patient, especially when the patient has developed a intraoperative bronchospasm. So that also can be definitely tried because of the presence of the reservoir bag. So another most important thing is it acts as a pressure buffer and prevents barotrauma. So whenever there is an obstruction beyond the system and towards the patient, suppose if there is a pressure gets built up, this pressure should not be transmitted to the patient. So that's how, the presence of the bag will prevent this. So you can see here the bag is distending. So when the bag distends, the pressure inside initially, you just look at this graph. So horizontally is the volume inside the bag and vertically is the pressure. So when the pressure, initially the pressure starts developing very rapidly and it may reach just about 30 centimeters of water. And afterwards, the pressure starts stabilizing and then later it starts dropping. Though, the volume inside the bag is increasing and it is distending the bag. So this is again based on the application of the Laplace law. So we know that the Laplace law says that the pressure is directly proportional to twice the tension and inversely proportional to the radius. So here the tension is because of the thickness and the material that is used for the bag. So, and it is a constant thing. So since the tension is a constant thing, as the radius inside the bag starts increasing, the pressure automatically falls. So the standard requirement of the maximum pressure that can occur in these bags is when they are distended to 4 times their volume. If the bag is more than a 1.5 liter one, so the maximum pressure should not go beyond 60 centimeters of water. And if the bag size is less than 1.5 liter, then the maximum pressure should not go beyond 50 centimeters of water. Next, we will discuss the breathing tubes. The breathing tubes are corrugated tubes. So how the corrugation of these tubes will help? Again, this is a question for the postgraduates in the exam. So why the tubes have to be corrugated? So one thing is because of the corrugation, there is increase in the flexibility. Second thing is, the corrugation will definitely prevent kinking. And, sometimes it is also said because of the corrugation, some amount of turbulence of flow occurs inside these tubings. And because of this turbulence, there will be a better mixing of gases because we are giving multiple gases like oxygen, nitrous oxide or air, and also the inhalation anesthetic agents. So all these gases have to be properly mixed before being delivered to the patient. And these breathing tubes, they are made with different kinds of materials. So in our time, so the rubber, majority of the breathing tubes were made of black rubber. And of course, later on, what we have presently, we have plastic and silicone breathing tubes also. So what were the advantages of rubber tube was it could be reusable. So the rubber tubes were reused, but there were a lot of disadvantages with these rubber tubes. One thing was they used to be very heavy and they themselves used to drag on the endotracheal tube. Second thing, they are opaque, and because of their opaque, so what is there inside was not be able to be seen. The next thing is, the compliance of these tubes used to be very high. So because of this increased compliance, so whenever the IPPV is done, so with a positive pressure, they could distend more and could accommodate more gas inside, and whatever the gas of the tidal volume should have been going to the patient now gets inside the breathing tube just to distend these breathing tubes. So suppose I am giving 500 ml of tidal volume, if 200 or 250 ml remains in the tube just to distend these tubes, patient may be getting only 250 ml. So that is the reason the compliance of these tubes should be very low. So that is a problem with rubber tubes. Another problem with the rubber tube, because the rubber gas solubility coefficient of inhalation anesthetic agent is so high, so they used to take in most of the inhalation anesthetic agent. So the concentration that is delivered at the vaporizer outlet may not be the concentration delivered to the patient. So these were all the problems associated with rubber. Of course, with silicone tubings, all these problems were not there. Only thing is silicone, the advantage of silicone tubes is they could be autoclavable. So you can autoclave them and reuse. But the problem with silicone tubes is their weight. They can drag on the endotracheal tube. So presently, most of us are using the disposable plastic tubes. So there are a lot of advantages with these disposable plastic tubes. So one thing is, these tubes are transparent, so better visualization of the interior. They are very lightweight, and so they don't drag on the endotracheal tube. So, and the other thing is they absorb less halogenated agents because the absorption is minimal. So because of their lower compliance, so decreased compressible volume will be there. So wastage of gases just to distend the tubings is also prevented. So what is the compliance of these plastic tubes? It's a very low compliant tubes. The compliance is just 0.7 ml per centimeter of water per meter. Suppose I am ventilating a patient with a peak inspiratory pressure of 20 centimeters. So 20 multiplied by 0.7 is just 14 ml. So that means only 14 ml is lost to distend the tubings, which is called as a wasted ventilation, and majority of the tidal volume that whatever I have fixed would be delivered to the patient. So there is an advantage with the plastic tubings. And they also hold 1 meter of that will hold about 450 ml, that is the capacity. And they also have a minimal resistance. That's what I was talking to you about when I was talking about the requirements. So the resistance offered by these 22 millimeter, the breathing tubes, is just about 0.5 centimeter of water per 30 liter per minute of flow. That means the resistance offered is very, very low. So the length of the corrugated tubes. So usually in majority of the circuits, what the most common circuits, what we use is a Mapleson A circuit and the Bain circuit. The Mapleson A circuit, usually the length is again 110 centimeters. Again, it's an exam question for you. And in the Bain circuit, it's about 180 centimeters. So why it is longer in Bain circuit? You can even have a longer than this also. But usually why 180 centimeter? Because inside there is one more tube is there, which is carrying the fresh gases. The outer tube is the one which is producing a reservoir for the expired gases. So it should have a capacity or equal to about 1 tidal volume of the patient. So usually this 110 centimeter and 180 centimeter of a Bain circuit will have a capacity of 500 ml. So why this is important again, when you leave a patient on spontaneous ventilation, so the breathing tube, the corrugated tube should act as a reservoir for the expired tidal volume, so that the expired tidal volume should not reach the bag when the patient is breathing spontaneously, especially with the Mapleson A circuit. So this is again one of the questions that is asked for you in the exam. Now coming to the next component, the APL valve. So adjustable pressure limiting valve. So this adjustable pressure limiting valve in the olden days was called as a heat brake valve. So usually this contains the spring-loaded disc, and usually when you want to allow the patient to breathe spontaneously, you have to completely keep it open, and the disc will be there, and it will be closing the valve by coming down on the seat. So whenever there is a pressure is built up inside, the disc will move up and allow the gases to move out. So when you want to control the ventilation, this valve has to be partially closed. So only when sufficient amount of pressure is built inside, then only it will open. So what is the resistance offered by these the valve? So it offers a resistance when it is completely open. The resistance offered by these valves is about 1 to 5 centimeters of water. That is why in a pediatric circuit, we ideally should not have the valve, because if you are allowing the child to breathe spontaneously, because even that 1 centimeter of resistance may not be able to be countered by the work of breathing of the child. It has to increase the work of breathing, and the problems can start. Now, the other most important thing, again, for the exam purpose, is the classification of the breathing systems. So again, there are multiple classifications have been done over the years. So a lot of confusion as far as classification is concerned. So for the exam going postgraduates, 2 classifications is more than sufficient to be known. So one is the DRIPS classification, and another is the modified Conway's classification. So the DRIPS classification is mainly done based on the volume of reservoir that is present in the breathing system, and also how much of rebreathing occurs in a particular system. So based on that, DRIPS has classified. So let us discuss about this DRIPS classification, because I have seen many times as an examiner, whenever I have asked the students, invariably they talk about the DRIPS classification only. Like they'll start telling They are classified as open, semi-open, semi-closed, and closed circuits. So nowadays, ideally, because there's a lot of confusion with this classification, you can also tell about if the examiner asks you, but better to talk about the Conway's classification. I'll come to that also. So as far as DIPS classification, open circuit means no reservoir, no rebreathing. Semi-open means good reservoir, no rebreathing. Semi-closed means good reservoir and partial rebreathing. And closed circuit is absolutely total rebreathing is used, minus carbon dioxide, of course, and a good reservoir. So what are the examples he gave for each of these? So open circuit, actually the example was the Schimmelbusch mask. You all know that how confusing it is, because when you're using a Schimmelbusch mask, you won't use any, the machine at all. So if you're not using a machine, and how can you describe this as a breathing circuit? The second, the semi-open circuit, all these Mapleson systems were classified by DRIPS as the semi-open systems, and semi-closed is the one is the closed circuit with an absorber. When the APL valve is partially open, then you call it as the he called it as semi-closed, and when it is completely closed, then the circuit was called as the closed circuit. So, but as I told you that there were a lot of classification problem with this classification by DRIPS. So that's why at present the best thing would be to go for functional classification. So that is done by the Conway's classification, that is a modified Conway's classification. So with this, basically the breathing systems are classified based on whether there is a provision for carbon dioxide absorption is there or not. Suppose the breathing systems without carbon dioxide absorbers or with carbon dioxide absorbers. So again, each one of them have been classified as having either whether they have a unidirectional flow or a bidirectional flow. Breathing systems without carbon dioxide absorber, the examples for unidirectional flow is a circle system when you are not using or when you have bypassed absorber. That becomes a breathing system without carbon dioxide absorber, unidirectional flow. But otherwise, the most other example is the systems which have got a non-rebreathing valves. So that is the unidirectional valves, unidirectional flow without carbon dioxide absorption. So the bidirectional flow is all these Mapleson A to F, Humphrey ADE, enclosed afferent reservoir. So these are the examples for bidirectional flow. Again, coming to the breathing systems with carbon dioxide absorption, again subclassified as unidirectional flow and bidirectional flow. Unidirectional flow is our circle system, which every day we are using. So bidirectional flow was the to and fro system, which was introduced by Waters. So let us discuss about each one of these things. Of course, circle system without absorber, I need not have to discuss. I'll discuss with regular circle system with the unidirectional flow. So non-rebreathing systems. So they were also being used initially. So these non-rebreathing systems, it is just like a Mapleson A circuit or a Magill circuit, wherein you replace the expiratory valve or the APL valve with a non-rebreathing valve. So once you replace a non-rebreathing valve, so it becomes a system with non-rebreathing valves, or the system without carbon dioxide absorption with a unidirectional flow. Many times one of the questions that used to be asked is that suppose if you have a Magill circuit, so how do you use for controlled ventilation? So definitely you can change it to a non-rebreathing valve and then control the ventilation with a Mapleson A circuit also. So now coming to these, how do they function? So suppose if it is a non-rebreathing valve is there and the patient is left on spontaneous ventilation. So what will happen is during spontaneous ventilation, as the patient creates a negative pressure, all the fresh gases will go to the patient. And when he expires, because the expiratory unidirectional valve will open and the inspiratory valve will close, so all the expired gases will move out of the patient. So the minimum fresh gas flow you have to keep is equal to 1 minute ventilation. So as long as you keep 1 minute ventilation as a fresh gas flow, there won't be absolutely no rebreathing. But if you keep less than 1 minute ventilation, there is a high chance of rebreathing of gases by the patient. So suppose the controlled ventilation, So the valve most commonly used are many of these valves like Rubin valve, Stephen-Slater valve, the Fruman valve, Ambu valve, all these are usually used. So that's how, I was telling you, how do you convert Mapleson A circuit for controlled ventilation? You can take the non-rebreathing valve from the Ambu bag, and then you replace that valve from the expiratory valve of the Mapleson A. It can be used for even controlled ventilation with 1 minute ventilation. So here what happens is during inspiration, because we are going to compress the bag, the high pressure is created. That is going to move the non-rebreathing valve towards the expiratory side, and it will block the expiratory port, so that all the gases will go to the patient. During expiration, the valve will come back and then block the inspiratory side, and all the expired gases will move out. So one of the valves I was talking to you about is the Rubin valve, which was very popular. So the color coding is there with the Rubin valve. Sometimes you may be asked. So the color coding of Rubin valve is blue is for the bag, because many times we'll be using for resuscitation purposes. So we'll be using an Ambu bag. So that's how the blue side of the Rubin valve is connected to the Ambu bag, and the red is for the patient and yellow for the expiration. So coming to what are the disadvantages, why we are not using these systems with non-rebreathing valves, there are a lot of disadvantages. One is, the fresh gas flow has to be altered repeatedly, because, the minute ventilation of the patient, it cannot be always constant. It can keep changing. So the other thing is there is no mixing of gases, so no humidification, no conservation of heat. And, they are also not convenient because they have to be close to the patient, and the bulk itself can produce drag on the endotracheal tube. And many times they can malfunction, and once they malfunction, it will be, a disaster for the patient. Now coming to the circuits without carbon dioxide absorption with a bidirectional flow. So these circuits with a bidirectional flow without carbon dioxide absorption have been classified as afferent reservoir systems and efferent reservoir systems. So what do we mean by afferent reservoir and efferent reservoir system? So we have in the breathing system afferent limb and the efferent limb. If the breathing bag or the reservoir bag is placed in the afferent limb, it becomes an afferent reservoir system. And if the reservoir bag is placed in the efferent limb, then it becomes an efferent reservoir system. Just let me give you an example now. This is a Mapleson A circuit. What is the afferent limb of this? So you have the afferent limb from the fresh gas flow to the patient is called as the afferent limb. So here you have got a long afferent limb, and the breathing bag or the reservoir bag is connected to the afferent limb. That is why Mapleson A is called as the afferent reservoir system. So the efferent limb is from the patient to the expiratory valve. So this is a very short limb in Mapleson A circuit, and we are not connecting the back to this efferent limb. That's why it is an afferent reservoir system. Now coming to the efferent reservoir system. So the Mapleson D is actually an example for efferent reservoir, because I was telling you again the efferent limb and the afferent limb. So here the afferent limb is very short. Afferent limb is from the fresh gas flow to the patient. So this is very short, and the breathing bag has not been connected here. Whereas the efferent limb is from the patient to the expiratory valve. We know that in case of the Mapleson D, the APL valve is not very close to the patient like in Mapleson A. It has been shifted very close to or away from the patient and very close to the bag. And the fresh gas flow has been brought very close to the patient. So the efferent limb, that is from the patient to the expiratory valve, is very long, and it also acts as a reservoir, and we have connected the back to the efferent limb. That's why it is an efferent reservoir system. So what are the examples for afferent reservoir system? So we have the Mapleson A and the Mapleson B and Mapleson C. Actually, to tell you frankly, that Mapleson B and Mapleson C cannot be considered as afferent reservoir systems, because you just see here in the Mapleson B, the fresh gas flow has been shifted from away from the patient to very close to the patient, just proximal to the expiratory valve. So the afferent reservoir, afferent limb is also very short, afferent limb, and the efferent limb is also very short from the patient to the expiratory valve. So again, the same thing in Mapleson C, where it is same like Mapleson B, except that there is no corrugated hose. So that is why they have been renamed as junctional reservoir systems. So coming to the efferent reservoir systems, so we have the Mapleson D, E, and F are the examples for efferent reservoir systems. So Mapleson E and F are actually, we can say, the modifications of Mapleson D system. So let us move on to the functional analysis. Again, very important for the practical exam or even theory exam. You will be asked many questions on this functional analysis of these systems, especially the Mapleson systems. So let us discuss about these things. So before actually discussing the functional analysis, few things you have to know before you go for actual analysis of these functions. So one thing is, every respiratory cycle has got 3 phases. You should always remember the inspiratory phase, the expiratory phase, and the expiratory pause. So during, expiration, so which is more important for us. So the first gas to come out is the dead space gas. The next is a mixture of dead space and the alveolar gas. And the last one to come out is the alveolar gas. Another thing which should always, talk when we talk about the functional analysis is, so what kind of a breathing the patient is on, whether he is on a spontaneous breathing type of ventilation or he is on controlled ventilation. So in spontaneous ventilation, you should always remember that the APL valve has to be completely kept open. And also you should remember that it only opens during expiration and it will always be closed during inspiration. That is in spontaneous ventilation, because the negative pressure that is created during inspiration, always keep it closed. And it only opens during expiration, that too when the bag fills and sufficient pressure is created. So these are very important to understand the functional analysis. So the next thing is, during controlled ventilation, the valve is kept partially open and it only opens during the peak of inspiration as the bag is squeezed. That means when the bag is squeezed, immediately it will not open, and when the sufficient amount of pressure is created, that too in the peak of inspiration, then only the valve will open. So another thing is about some of the factors which can influence rebreathing. That also we have to know about. So these are the factors like fresh gas flow, how much we keep, the respiratory rate of the patient, expiratory pause, and tidal volume. So when you leave the patient on spontaneous ventilation, we have no control over the respiratory rate, expiratory pause, or the tidal volume. We can only control the fresh gas flow. Whereas when we actually go in for controlled ventilation, we can control all the 4 things. We can control the respiratory rate, expiratory pause, the tidal volume, and fresh gas flow, so that definitely we can alter the amount of fresh gas flow that is required during controlled ventilation. Now coming to the functional analysis of the individual breathing circuit, let us discuss about the Mapleson A circuit. Again, I told you that whenever we discuss, we always discuss what happens during spontaneous ventilation and what happens during controlled ventilation. So during spontaneous ventilation, the initial thing is we fill the whole system with the fresh gas flow, and the APL valve is always kept completely open. But what happens during inspiration, when the patient takes a breath, the expiratory valve will not open because the patient is creating a negative pressure. The patient can draw the fresh gas flow from the bag, so the bag collapses. So what happens during expiration, which is very important for us, is during expiration, the expired gases start moving out. The first gas to come out is the dead space gas, followed by the alveolar gas. Because I was telling you this, the corrugated hose can accommodate nearly 1 tidal volume of the patient. So majority of these gases may not be able to reach the reservoir bag. So in the meantime, the reservoir bag starts getting filled with fresh gas flow. Once the reservoir bag is filled, sufficient pressure is created to open the expiratory valve. So whatever the gas which is close to the expiratory valve, that is the alveolar gas, will start moving out, and this continues during the expiratory pause, so that all the alveolar gases will move out. Next, the whole system will be filled by fresh gases and also the dead space gases which have not taken part. They are as good as a fresh gas flow, so that will be breathed by the patient. So as long as you just keep 1 minute ventilation for the fresh gas flow, or even equal to alveolar ventilation, that is more than sufficient for Mapleson A circuit. That's how Mapleson A circuit is an ideal circuit for spontaneous ventilation. Let us see what happens during controlled ventilation. So during controlled ventilation, the APL valve is partially open or partially closed also, you can say. So when the first breath, when the bag is squeezed, so all the fresh gas flow will go to the patient and some amount of the fresh gas flow also leaks out because at the height of the inspiration, as we increase the pressure, the expiratory valve will open and then the fresh gases also move out. So during expiration, what happens? During expiration, because we'll be giving sufficient time, even the dead space gas and the alveolar gas will start moving and even they may fill the bag because the APL valve is partially closed and unless a high pressure is created, it will not open. So during the next the inspiration, as the bag is squeezed, so whatever the close to the patient is the alveolar gas, all the alveolar gas will be going to the patient, and because immediately the APL valve will not open till a sufficient pressure is created. When the sufficient pressure is created, most of the fresh gases and also the dead space gases may go out of the APL valve. That means with the controlled ventilation, so the patient can have a lot of rebreathing of the carbon dioxide containing alveolar gases. So even though we may have to keep 3 times the minute ventilation for the controlled ventilation with Mapleson A, still there may be rebreathing of carbon dioxide. That's why it's a worst circuit for controlled ventilation. Coming to the advantages and disadvantages of the Mapleson A. So as I told you, ideal for spontaneous breathing is the only advantage. A lot of disadvantages because the valve, the expiratory APL valve is close to the patient. Because of this valve is close to the patient. So one is the difficulty in accessing by the anesthesiologist. And second thing is, it can drag on the endotracheal tube because it is quite bulky. And the third is scavenging is not possible. So these are the disadvantages. So let us discuss about the Mapleson D circuit, which when I discuss about Mapleson D, the functional analysis is same for E, F, and also the Bain circuit. So what happens with the Mapleson D for spontaneous ventilation? So again, here the fresh gas flow is very close to the patient. Valve is quite away from the patient, just near the bag. And also the expiratory valve has to be completely kept open. So what happens during inspiration is all the fresh gases will go to the patient. During expiration, the dead space gas and alveolar gas starts moving. In the meantime, the fresh gases are also pushing these expiratory gases, especially the dead space gases and the alveolar gas, towards the bag. So as these gases are being moved, so because, unless the fresh gases are in sufficient quantity, these gases may not reach the bag. So what happens is when the patient takes a breath, the patient may be breathing the expired gases or the alveolar gases. So for that, unless you keep a high fresh gas flow, then only all these gases can be pushed to the bag. And once the bag fills, the expiratory valve will open. And then the alveolar gases can be pushed out, and whatever that the remaining part of the system towards the patient, which is filled by the fresh gas flow, will be breathed by the patient. So that is the reason for spontaneous ventilation, you have to keep a flow of at least 200 ml per kg body weight or equal to twice the minute ventilation in Mapleson D circuits. Let us see what happens in controlled ventilation and how it is more efficient during controlled ventilation. One thing I want to tell you during controlled ventilation, you have a total control over the expiratory phase and the expiratory pause and also the tidal volume. So again, during controlled ventilation, so we keep the valve semi-closed or half-closed. So when initial breath, when we squeeze the bag, all the fresh gas flow will go to the patient and some fresh gas flow will also move out of the expiratory valve. But what happens during expiration is as we give quite a prolonged expiratory time and also the expiratory pause. So what will happen is whatever the fresh gas flow that is entering is able to push all these gases, the alveolar gas and the dead space gas into the bag. So once after giving sufficient amount of expiratory pause, when the bag is squeezed, so most of the alveolar gas will move out and the remaining part of the breathing system, which is filled by the fresh gases, will be delivered to the patient. So that's how, it's a lot of advantages there with Mapleson D for controlled ventilation, and the requirement of the gases is just equal to either 1 minute ventilation or even equal to alveolar ventilation of just 70 ml per kg body weight. That's how the advantage of the Mapleson D. So just discuss about all the advantages of Mapleson D circuit. So they are ideal for controlled ventilation because the expiratory valve is away from the patient end and it's easily accessible. And also because of that, scavenging also of the expired gases is possible. Only disadvantage, of course, may not be ideal for spontaneous ventilation, but even then it requires just 2 times the minute ventilation. So definitely you can use it for both spontaneous ventilation and controlled ventilation if you don't have Mapleson A circuit. So sometimes you will be asked a question. So which Mapleson circuit is ideal for spontaneous and which one is ideal for controlled ventilation? So better to remember this mnemonic. So all dogs can bark. That means ADCB. That means for spontaneous ventilation, best is A circuit and the worst is B circuit. And for controlled ventilation, the mnemonic is dead bodies cannot argue. That means DBCA. D, Mapleson D is best for, and also E and F and Bain circuit are ideal for controlled ventilation. A probably is the worst circuit for controlled ventilation. So coming to the Jackson-Rees modification of IHTP's circuit, that is the Mapleson F, or otherwise we always call it as pediatric circuit. So this functional analysis is same as Mapleson D circuit. Whatever we had just discussed about the Mapleson D, because this is a modification of Mapleson D, it is same. So what are the fresh gas flow requirements for these? Again, for spontaneous ventilation requires higher fresh gas flow, and controlled ventilation, just 1 minute ventilation is enough. But one thing you should remember, whatever may be the minute ventilation, even if it is less than 3 liters, but the minimal fresh gas flow you have to keep to prevent rebreathing for this system is 3 liters. So suppose if it is higher than 3 liters, then you just keep it to 1 minute ventilation. But if the minute ventilation of a child, say for example, 4 kg child, 5 kg child is very low minute ventilation, but still you can keep it to 3 liters as the fresh gas flow. So what are the advantages of these? Many times you will be asked, mainly, lightweight, minimum dead space. Lightweight is very important in pediatrics because, many times you will be using a cuffless endotracheal tube. Easily it can come out. So another thing is the dead space is minimal. The dead space, I'll be touching it in the next slide, apparatus dead space. And also it has got a minimum resistance because ideally it should be valveless. And it can be used up to 20 kg body weight because the volume of the car, sometimes you will be asked why only up to 20 kgs, why it cannot be used for a larger child. It is because the corrugated hose has got a volume of 150 ml. I just said that ideally the corrugated hose should be having a reservoir of equal to 1 tidal volume. So in a child, 7 ml per kg body weight, so it will be about 140 ml. So that is up to 20 kg. Definitely this pediatric circuit can be used. So what are the disadvantages of that? Need high fresh gases. As I said that, 3 liters is the minimum. So if there is any occlusion of this overflow valve, there can be barotrauma, and usually there won't be any humidification of the gases with this system. So coming to I was talking to you about the apparatus dead space. Sometimes you are asked about this apparatus dead space also because, one way of producing hypercapnia is increase in the apparatus dead space. Because normally when we say hypercapnia, it can be because of increased production of carbon dioxide or decreased elimination of carbon dioxide, that is hypoventilation. But in anesthesia, we also know that any increase in dead space can increase the rebreathing of carbon dioxide and can produce hypercapnia. So in different systems, it is defined as the volume of expired gas containing carbon dioxide present in the circuit, which can be rebreathed. So till that level, so rebreathing of expired gases with carbon dioxide can occur. Beyond that, there won't be rebreathing of expired air containing carbon dioxide. So in a Mapleson A circuit, it is from the patient to the expiratory valve. So till here, there can still be chances of rebreathing of expired gas containing carbon dioxide. In a Mapleson D circuit, D, E, and F, and also the Bain circuit, it is up to the entry of the fresh gas flow. And in case of the closed circuit, it is up to the Y piece. Still, there mixing of expired and inspired gases can occur, and there is possibility of some amount of rebreathing of carbon dioxide containing gases. Coming to the coaxial circuits, you know that we have two coaxial circuits. Coaxial means a tube within a tube. So Bain's and Sporel circuit was introduced in 1970, modified Mapleson D, and Lack circuit was introduced in 1976 by Alistair Lack. So it is a modification of Mapleson A. So why this Lack circuit was required? Because during those days, so many patients used to be left on spontaneous ventilation. We know that the Mapleson D circuits, including Bain's circuits, may not be ideal for spontaneous ventilation. So that's the reason why Lack thought that a modification of the Mapleson A is required. And the lot of here Mapleson A circuit, we had the expiratory valve very close to the patient. What the Lack system has is through the inner tube, we have the expired gases coming out, and the expiratory valve could be shifted from close to the patient to away from the patient. So the advantage here is, one can have an accessibility to the expiratory valve, and also the scavenging was possible. That's how, the Lack system was introduced. But when it was introduced, because, the inner tube was of small diameter, so there was an increased resistance offered for expiration. So that's how later Lack had to modify it. He increased the inner tube to 15 millimeters and the outer tube to 33 millimeter. That's how it was solved. But nowadays, we hardly use the Lack circuit much, because we don't leave the patients on spontaneous ventilation. Majority of the times we control the ventilation. For controlling the ventilation, Lack circuit is also not an ideal circuit, and we have better circuits for controlling the ventilation. So coming to the Bain circuit, here the change from Lack is, the one thing is a modified Mapleson D. Another thing is, through the inner tube, we have the fresh gases, and through the outer tube, we have the expired gases. So, and the inner tube will be very close to the patient. That's how the apparatus dead space is very, very small with Bain circuit. So the inner tube diameter of the Bain circuit is about 6 millimeter. Outer tube is 22 millimeter. So because of the Bain circuit, it's so popular all over the world. It is still one of the very popular open circuit that is being used nowadays. And there are a lot of advantages of Bain circuit. See, one is it is lightweight. Anesthetist can stand at a distance. Warming and humidification of inspired gases can occur because there is some amount of mixing of expired and inspired gases. Plus, through the inner tube, we have the fresh gases. Through the outer tube, the expired gases, which are warm, can also heat up the fresh gases that are going through the inner tube. And scavenging is also of exhaled gases is possible. But there can be a lot of hazards also with the Bain circuit. The most important hazard is the inner tube. If it gets disconnected, the whole of the outer volume of the outer tube can become a dead space. There are so many case reports with the Bain circuit where it has not been properly checked and used, and the inner tube has been disconnected, and invariably the patient will not get up because of the hypercarbia. So the patient can have carbon dioxide narcosis. So that is one thing. So before using the Bain circuit, you have to test for the integrity of the inner tube. So what are the tests that are done to know the integrity of the inner tube? First of all, we know that the outer tube of the Bain circuit is transparent. The inner tube is opaque and it's usually green. So in one of the conferences, one student had asked me why it is green. Probably, it was invented in US. There, the oxygen is colored green. That's why the inner tube being the fresh gas flow carrier, that was the reason why it was made green. So you just, keep it against light and you can easily see the inner tube. Any grass disconnections, you can easily see through the outer tube. So second test is called as a Feeks-Crompton-Smith test. So here, to check the integrity, what we have to do is you just start about 3 to 4 liters of oxygen in the flow meter. Then you close the expiratory valve of the Bain circuit. Now you try to occlude the inner tube with a with your little finger. So if you try to occlude the opening of the fresh gas flow, that is the inner tube, so the back pressure should be carried to the flow meters and there should be a dipping of the bobbin. So with later Ganesh modification, instead of using our finger, many times our finger may not go through the outer tube to block the inner tube. So what he did was he used a barrel of a syringe. So that is called as a Ganesh modification of Fields-Crompton-Smith test. So I'm just showing you a video of this particular test, how to do it.
Going to block the inner tube with the syringe, barrel of the syringe. Just observe there.
What I'm doing, maybe the audio may be, I'm just
this shows that
the barrel of a
integrity of the
just blocking.
Now if I take out my finger from the barrel of the
bobbin, so whenever I block, the bobbin is moving. And another is Ganesh modification is
it will be hissing noise. This is called as a Ganesh modification of Fields-Crompton.
Unfortunately, because the audio is so low, you are not able to hear the hissing noise. So then another test that is the popular test is the Pathix test. In the Pathix test, so what you have to do is, again, you have to close the expiratory valve, and what you have to do is you have to occlude the outer tube also with a thumb. And you can start about 3 to 4 liters of oxygen, or you can fill the bag using the oxygen flush. So what you have to do now is, now the bag is filled, the expiratory valve is closed, and you have to do simultaneously take out your finger from the outer tube and also activate the flush. So here the Venturi effect will, will be the one which occurs. And because of the Venturi effect, here as I activate the flush, nearly 70 liters of oxygen will start flowing through a narrow opening of the inner tube. Because of that, we know that Venturi effect is when any flow encounters a narrowing, the pressure drops and the velocity increases. That is a Bernoulli's principle and also the Venturi effect. So here suddenly there is so much of pressure drop occurs. Whatever the gas that is there in the bag, it gets sucked in through the outer tube and the bag will collapse. So you can see the other second finger where there is, the integrity of the inner tube is lost there, and that's how there is the bag remains, distended. So just let me show you this particular.
So then you have to close the APM valve and also close the outer end of the vein circuit.
So what I'm doing is I close the.
For this, you can also use
opening of the outer tube.
flush
also I've closed the expiratory valve. I've used the flush
the APM valve is closed.
And now I'll do two things simultaneously. I'll open my finger from the outer tube, and also I'll activate the flush.
I'll be
Just see
activating the flush, and also I'm opening the finger from there.
See, the bag is collapsing.
The
bag is collapsing provided the inner tube is patent and then integrity is complete. So that's how you can always use this test. So many times you will be asked to demonstrate this test in the exam. So coming to Waters to and fro circuit, already I have told you about this Waters to and fro circuit, and the advantages being it's made of steel and could be sterilized by autoclaving. But there are a lot of disadvantages why it did not become popular. Well, many disadvantages, like it has to be kept very close to the patient, and also the heat generated will heat up the canister and it can even produce burns to the patient. And then, the channeling can decrease the efficiency of soda lime. What happens is, since it is to be kept horizontal, so because of the gravity, the soda lime will start, coming down, and there can be a lot of space above the soda lime, and, the gases can directly go bypassing the soda lime, and there can be a lot of rebreathing can occur. And the other thing is quite heavy and can drag on the endotracheal tube. Now coming to the closed circuits. So just let us discuss about the components of the closed circuits. So you can see the closed circuit has a Y piece, then you have the inspiratory limb and then the expiratory limb, so that is a corrugated hose, and you have the the inspiratory unidirectional valve and the expiratory unidirectional valve. You can see this is the inspiratory and expiratory unidirectional valve. You have the fresh gas flow entry is also there, the canister. Then we have the reservoir bag, then the adjustable pressure limiting valve or APL valve, and also we have the 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 auto switch, manual to the ventilator switch. So once you go to the auto, so automatically the bag gets bypassed and the gases will go to the ventilator. We also can have the scavenging system from the ventilator through the ventilator relief valve. So one common question for you that is asked in the exam is regarding the direction of flow of these gases. You have to demonstrate how the gases will flow. So that is, from the patient, the expired gases will flow through the expiratory limb, and then, the expiratory unidirection valve, it gets lifted up. So the gases will enter into the bag, and with the sufficient pressure, some amount of the gases will also flow to the expiratory valve. Then they pass through the soda lime, the carbon dioxide gets absorbed. The fresh gases are added on. So the gases will move through the inspiratory unidirection valve and go to the patient. So many times you can be asked about this, particularly to show the direction. So another thing will be asked about the position of these various components. So it's again a common question that is asked, but three principles you should always remember whenever you want to know where exactly the particular component has to be placed, where is the ideal position for the component. One thing is, the unidirectional valve should always be there between the patient and the bag. So because if the bag is placed, proximal to the unidirectional valve, that is towards the patient, then definitely you can produce a lot of rebreathing. So the second important thing regarding the fresh gas connection. So the fresh gas inlet should be on the inspiratory side, and it should be either upstream of the inspiratory unidirectional valve or downstream of inspiratory unidirectional valve. It should never be kept on towards the expiratory part of the circle system, because unnecessarily, again, the gases have to pass through the soda lime, exhaustion of soda lime can occur. The third thing is the position of the APL valve. So the APL valve should be between the expiratory unidirectional valve and the canister, so that the gases coming out after the expiratory unidirectional valve, so they should pass through the soda lime and the carbon dioxide should be getting absorbed. And in the meantime, any excess expiratory gases should flow out of the expiratory unidirectional valve. Suppose if it is kept on the inspiratory side, then all the gases will go through the soda lime, and some amount of the gases which have passed through the soda lime, which do not have carbon dioxide, are also wasted. So these three principles you should always remember about. Then coming to the unidirectional valves, how they function. So usually these unidirectional valves, they'll have two chambers, the inner chamber and the outer chamber. So the gases will, and also there is a very lightweight, the disc is there. And this disc is majority of the times is made of the mica, which is very, very light, with this smallest of amount of pressure can lift it. So as the gases move through the inner chamber, they lift the disc, and the gases will move to the outer chamber and move towards either towards the patient, depending on if it is an inspiratory unidirectional valve, or away from the patient if it is an expiratory unidirectional valve. And again, the top of the valve is covered by a removable clear plastic dome, so that the disc can be easily seen and also periodically cleaned or replaced. So whenever you are using these circle system, you can easily see the disc moving up and down with inspiration and expiration in each of the valves. So that's how you know that whether the valves are functioning properly or not. So when properly functioning, what is the resistance offered by these valves? So it's just about 0.31 centimeters or even less. So that is the advantage, because when I want to leave a patient on spontaneous ventilation, so these valves should not offer an increased resistance for the breathing by the patient. So why it's very important is, another thing is, the seal, that is the disc, is again, suppose if the unidirectional valve is not functioning properly, it keeps open, whether there is during inspiration or expiration, there can be a large volume of the circuit can become an apparatus dead space. That's the reason why these valves have to be checked before starting our anesthesia. Now coming to the other component is the canister. So in the olden days, we used to have this double chambered canister, and in the exam majority of the time, these kind of canisters will be kept. So two chambers are there simultaneously, one above the other. And we also have now the single chambered canisters are also available, and also we have these disposable canisters are also containing the soda lime are also available. So why, again, you have to know about the two chambers, because in the olden days, each chamber had a capacity to have 900 grams. That means each chamber 900 grams, two chambers 1800 grams. So nowadays, disposable ones even come with 500 grams or even 1 kg of the capacity. So again, this is important for us to know for exam purpose is, that how much of this soda lime can absorb the carbon dioxide. What is the capacity? That is one of the questions that is asked. Usually the capacity is about 26 liters per 100 grams. But majority of the times for all practical purposes, the soda lime can absorb about 20 liters per 100 grams. So now we know that the patient, that means when it is completely filled as a fresh soda lime, so 1800 grams can absorb over 360 liters. So now the patient, a 70 kg patient, will be breathing out 200 ml of carbon dioxide every minute, that is 3 ml per kg body weight. So that means for 1 hour, he'll be breathing out about 12 liters. That means if I'm using this canister, which is freshly filled, I can use it for 30 hours. Suppose I'm using a 1 kg canister, then I can use it only for maybe about half of this, about 15 hours. If I'm using only 400 or 500 grams capacity canister, then the duration of the total duration, I can use it maybe about 7 hours or 8 hours. So this is again important when you are planning a surgery, which is a prolonged surgery. Then coming to the absorbents. So we have various absorbents, soda lime, bara lime, Amsorb. The soda lime is even today, one of the most commonly used absorbent. It mainly consists of the calcium hydroxide, sodium hydroxide, potassium hydroxide, and water of about 15 to 19%. Calcium hydroxide is the main thing, about 80%. So because it also contains sodium hydroxide and potassium hydroxide, which acts as catalysts, so the pH of soda lime is very high. So it's almost more than 12. So because of that, it can interact with the inhalation anesthetic agents, which I'll be just discussing with the next 1 or 2 slides. So then again, bara lime, it does not contain sodium hydroxide or potassium hydroxide. It contains mainly the calcium hydroxide and barium hydroxide. Calcium hydroxide 80%, barium hydroxide 20%. So it is one of the most stable absorbent. But unfortunately, because the barium hydroxide is there, it can interact with desflurane and can produce, release carbon monoxide. So that is the reason why we don't use bara lime. Because of its stability, it is still used in spacecrafts for absorption of carbon dioxide in the spacecraft. So the third one, which is again the most popular, is nowadays it's becoming popular, is Amsorb, which does not contain sodium hydroxide or potassium hydroxide. It contains only the calcium hydroxide, near 80%, and calcium chloride. So what is the chemical reaction that occur with these? So usually the carbon dioxide combines with water in the soda lime to form carbonic acid. The carbonic acid reacts with sodium hydroxide to produce sodium carbonate and water. Again, there is a regeneration of this sodium hydroxide, but because sodium carbonate will react with calcium hydroxide to produce calcium carbonate and sodium hydroxide. So this is the usual chemical reaction when you are using the soda lime. But I was talking to you about the reaction of these inhalation anesthetics with the absorbers. So how do they react? When do they react? Again, this is a very important question for your exams. So when you're using sevoflurane, so whenever there is the temperature is very high, because as you continue to use this soda lime, that a lot of heat is generated. And second thing is when it gets desiccated and becomes dry, the soda lime. And third thing is when you are using a higher volume or higher concentration of the inhalation agent. Plus, if you are going in for a very low fresh gas flow, that is very low flow anesthesia. So then sevoflurane can interact with the absorbent and can produce a compound called as a compound A, which has been proved to be nephrotoxic in rats. So that is the reason a caution has been given whenever you want to use sevoflurane. If you want to go for low flows, it is better not to go below 2 liters ideally. But if you are having 2 MAC-hours, you can still go up to 1 liter. So that is a caution that is given. 1 MAC-hour is 1 MAC multiplied by the number of hours of the use. That is, if you are using 0.5 MAC, then 2 hours will be 1 MAC-hour. So maximum when you go for 1 liter fresh gas flow, then you can use it for 2 hours. So that is the caution for sevoflurane. And again, for desflurane especially, and again, when you are using desflurane, so whenever the temperature is increased, the dry soda lime, desiccated soda lime, and when the agent is being used higher, then again the desflurane can interact with soda lime to produce what is called as a compound A. So, sorry, what is called as the carbon monoxide. So the carbon monoxide, that it can produce a lot of problems for the patient. It cannot be detected by our regular 2-wavelength pulse oximetry also. And that's how it cannot be detected by us during the intraoperative period. So that's how, one syndrome that was described is called as a Monday morning sickness. So what is this Monday morning sickness? Is, if the anesthetist on Friday, because, many of the anesthetists in Western countries, they don't work on Saturday and Sunday. So they close the whole thing and then go off on Friday evening. Suppose if the anesthetist forgets to close the master switch and there is a particular provision of, minimum mandatory flow is there in that particular machine. That's what when we were discussing about the Anaesthesia Workstation, the minimum mandatory flow of oxygen was also discussed. So suppose if there is 200 or 250 ml of minimum mandatory flow is there, because the master switch is on, so 200 to 250 ml of oxygen will be going through the system, it will be going through the soda lime, and it will desiccate the soda lime. So on Monday morning, when the first patient is being given the, the anesthesia, so then the desflurane, if it is being used, it reacts with desiccated soda lime and produces carbon monoxide, which cannot be detected. And postoperatively, because of this carbon monoxide, patient may become sick. That's why it is called as a Monday morning sickness. Now with the AMSOR, I told you the active ingredient is only calcium hydroxide. There is no sodium or potassium hydroxide. And it also contains calcium sulfate and polyvinyl pyrrolidine for the hardness. And because of its, the pH is much lower when compared to soda lime, it won't generate any heat. And also there is no possibility of compound A or carbon monoxide. So it is very safe when we are going to use, sevoflurane or desflurane. Even you can go for sevoflurane probably less than 1 liter also. So again, the indicators are used to know whether the soda lime is exhausted or not. The most common indicators that are used in India is phenolphthalein and mimosa Z. If the fresh soda lime is white, then it is phenolphthalein, so it will turn to pink when it gets exhausted. And if it is red, it will turn to white. So that this is very important for us to know, because then only we know whether a particular soda lime is exhausted or it is fresh. Then again, sometimes you are asked about the size and hardness number of soda lime granules. So the size is usually described as 4 to 8 mesh, and hardness number is 75, because it should be sufficiently hard enough so that it should not become powder. Then it will increase the resistance for the flow of gases through the canister, and also this the powder can be pushed to the patient's lungs as well. So what are the advantages of closed circuit? One is economy, reduce pollution, and conservation of heat and humidity. The most important, the advantages, so that we can definitely go for low flows with these. So disadvantages are, because multiple components are there, can produce some amount of resistance. So these multiple components can malfunction, and there can be quite a bit of problems because of this complexity, and it requires quite a bit of vigilance continuously. So these are some of the disadvantages. And lastly, to the circle system check, because Dr. Anish was discussing about the apparatus check. So before actually using the circle system, it is always better to check for every patient. So very simple test. So these tests are mainly to check whether there is any leak is there or there is any obstruction to the flow. That's why these tests are called as the leak test and the flow test. So you have to thoroughly check before you start your case. So the leak test is what we do is we just close the Y-piece and then pressurize the whole system to about 30 centimeters and then just wait for about 10 seconds. If the pressure in the pressure gauge maintains to that 30 centimeters, that means there is no leak in the breathing system. And the second thing is the flow test. That is, if you can just take the Y-piece in your mouth and then try to breathe. So if you can't breathe through it, so that means the patients also cannot breathe. So this is the flow test, but individually also you can check for the individual unidirectional valves. So you just take out the Y-piece, and after taking the Y-piece, if you are breathing through the inspiratory limb, so you should be able to only inhale, but you should not be able to exhale, provided the inspiratory unidirectional valve is functioning properly. And you try to breathe through the expiratory limb, you should be able to breathe only, you should be able to exhale, but you should not be able to inhale, provided the expiratory unidirectional valve is functioning properly. So just to summarize things, knowledge about breathing circuits is very important, and you can be very safe to the patient by knowing more about these breathing circuits. And of course, for as long as the open circuit, the vein circuit is most popular, and it is also called as a universal circuit because it can be used for both spontaneous controlled ventilation for adult patients and also for pediatric patients. And closed circuit with absorber helps in the economy of gases and decreasing the atmospheric pollution. Thank you. Thank you so much.
Thank you, sir, for your wonderful presentation.